Hello and welcome to this presentation on projectile motion.
A lot of these presentations that I created, I read the words that are up there to the students. But for this one, I think I was pressed for time because obviously I was a full time teacher and I had kids at home and a life that I couldn't get everything accomplished and fully polished the way I wanted to. But this what I wanted to do was I wanted to create presentations. I used Articulate Presenter with PowerPoints where all you do is like talk and you just see the PowerPoint slides. And I've I've shown a presentation that I created using Macromedia Flash where I created something like Articulate Presenter. And what I wanted to do was I wanted the kids to go through a animated tutorial to gather information, but also have the ability to play around with it. And so since this was about projectile motion, I put this little cannon here on the graph, and this cannon follows the mouse around, and then the farther the mouse is, the faster the projectile comes out. The closer it is, the slower it is. So kids can spend a little time playing this out. And something about these presentations where the students were always handed a piece of paper where they were supposed to answer questions. So here it says a projectile is any object that is projected by some means and continues in motion by its own inertia. And more than likely, the worksheet that went with this, it would say, what's a projectile? Because this was freshman physics or any physics where you start this conversation of two-dimensional motion. You say, oh well, it's a projectile, and students aren't clear exactly what that terminology means. So they went through the workshop. They would either listen to me read these words, or they would read them themselves, and then they would answer the questions for every slide. So every slide, kind of just like a PowerPoint, like if you did a regular class lecture, there was information every slide that the students needed to write down. And then this is just to show how the green object is an object in projectile motion, the red object is an object in free fall, and the blue object is an object that's just moving horizontally. And we've already talked about vectors, so they know about horizontal vectors and vertical vectors, and they're getting this idea of breaking a single vector into its components, its x and y, or horizontal and vertical components. And now with projectile motion, what we have going on is that this object is accelerating and this object has a constant velocity. So they're going to see this in different ways just to scaffold what that means. Alright, so here we see how these line up in the graph. This one is constant velocity. This velocity is changing. Now we're going to take this and we're going to turn it into the equations, the mathematical formulas that we use to solve these problems when we have them on a test. Alright, we're going to use the acceleration due to gravity as 10 meters per second only, or per second squared, instead of 9.8 meters per second squared, because we were using the conceptual physics books by Paul Hewitt, and it's just so simple math, as we'll see when we plug in the formulas and get answers. Using the number 10, just like in the metric system, is so much easier than using a number 9.8, and you're basically coming up with the same answer. It's a theoretical answer because you're talking about no wind resistance, no air friction, and that number changes obviously due to the fluctuation in gravitational fields, whether you're on top of a mountain or whether you're in Death Valley. Also, whether it's a windy day, it's what's going to be the wind resistance causing an object to maybe reach its terminal velocity before it hits the ground. So here we see how easy this is. For 1 second, 10, 2, 20. So it's your velocity, your vertical velocity is the acceleration due to gravity, which we said was 10, multiplied by the time scale. So that's such simple math, right? 770. And we also have here a representation of the vectors taking place. So we could see these vectors as the numbers get larger. The vectors are represented in larger scales. And then this is the whole concept of the hammer and the feather dropped in a vacuum on the moon. Uh, they both hit the ground at the same time. The mass is irrelevant, and also if you throw or you have an object like a bullet, if you shoot a bullet and drop something at the same time, the bullet will hit the ground. This was on Mythbusters. This was the Mythbusters video was a great video to show this representation. That the bullet will hit the ground at the same time the object you dropped from the gun barrel hits the ground. And we did demonstrations in physics classes on this too, with an apparatus that shot a marble horizontally as a marble was just released to drop vertically, and you listen to the click click. We got our components being broken up here, so we saw these vertical components increasing as the object actually accelerated going downwards. Now we see that this vector does not increase in length because it's a constant. It remains constant. It's the same number. And then we have our equations here. So we see that this is one space, 1 unit space, 1 unit space. And we also see that this is representative 1 unit space all the way across. Now this is changed up, so the mouse doesn't interact with that. And obviously we could have just clicked on these, click, 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 click. They're wonderful buttons, but it's the keyboard buttons. So you can see that the speed here, as I hit the keyboard button, the speed increases or decreases, and then the horizontal or the angle can increase or decrease. But you'll see that the angle of this decreases or decreases. All right. So what the student's supposed to do here, obviously, observe the trajectory of a projectile by using the arrow keys to adjust its velocity and angle, and then press the space bar to fire. So, bam! Oh, that was it. So let's add some more speed there. Ramp it up. You can see increased speed, and you have a projectile, and we have a trace element that traces the path of that projectile. And then we come up with this fancy word, parabola. The trajectory is a parabola. And then they say, oh, this is what we talk about in math, a parabola. And then we talk about 45. So let's put this, I'm going to put this on a speed of 25. And we come up with this concept that, okay, so this is 82, and if I fire this, and now I want the speed to remain constant. And I could say, okay, well that landed there. And I could say, okay, this is 19, and I fire. Ooh, that landed way over there. And you're like, wow, that's pretty far. But what's the farthest one? And there you go. You see 45 degrees is much farther than higher or lower angles. And they can play with it. They can play with these angles, all different numbers. Sometimes the kids just sit there and just keep doing this until the board is all doodled up. Oh, and then we talk about the range being the same for when it adds up to 90 degrees. So we can go, or I got it at 25, so I'm going to hit this down to, let's do this at 25, and I shoot it. Okay, so that's way over there. And then 25 plus 65 is 90. And these should clip out at each other, so they go together there. And this is a game, so now we have a little gamification in here. Shoot the monkey game. Now the sheet explained that this projectile here is we're going to shoot a banana. This was a concept that was also in conceptual physics textbook, is that when I fire the gun, the hunter fires the gun, the monkey is scared and lets go of the branch and falls, and you want to shoot the monkey. So, maybe you want to do a speed of 32. When I hit the space bar, I missed the monkey. So I have this dotted line here, and I'm like, okay, well, I'll do that right there. Oh, I hit the monkey in the mouth. Well, what if my speed is reduced to 25? Well, I hit the monkey there. What if my speed is very high? I hit the monkey there. What if it's like super high? And his speed could be kind of infinite here. I hit him right in the face there. So, next slide, we have a question. Explains the reason. The reason you should aim right at the monkey, even though the monkey lets go right when you pull the trigger, is because both the monkey and the banana are in the air for the same amount of time before the collision. So, with respect to where they would have been with no gravity, they fall the same distance. And then this is the last part of projectile motion, is satellite motion, right? And this explains that a satellite is just a projectile that falls towards the Earth, but it doesn't hit the Earth; it just continually falls. So this satellite that's going around the Earth here is an object that's falling towards the Earth, and it never hits it. And then the students can fire. So that fell into the Earth. They're like, oh, let's increase the speed. And they can fire. And their objective is to get an object in orbit, right? And maybe they can't. They're like, I can't do that. And it says satellites are not free from the Earth's gravity. And then it tells you a little bit more. And then you have an equation. You have some numbers. 1 second for every 5 meters. 5 meters per second. So that's 5 meters for every 8,000 meters along the Earth's surface. Right, so the Earth's surface drops a vertical distance of 5 meters for every 8,000 meters. So we want to go 8,000 meters, 8 kilometers. So 8 kilometers per second. So that's giving them a hint. And then you hit it and you say, oh, look at that. Look at that. Whoa. Oh, look at that. I have an object. I just put that projectile in orbit, and kids can play with different angles and different speeds all they want. All right, and then we have it right. It has to travel 8,000 meters per second, and that we hit it at 8 kilometers per second. And that's the end of the presentation. Now, this obviously was paired with all types of activities, hands-on activities within the classroom, and demonstrations within the classroom also.